In this video, I work through this exam-style question on normal distributions, in which we're told a company produces cartons of milk. The volume of milk in milliliters that each carton contains can be modeled by a normal distribution with mean 1000 and standard deviation 4. In the manufacturing process, a carton of milk is rejected, in other words cannot be sold, if it contains a volume less than 995 milliliters. And following that information, we're faced with three things to do. The first of which, we need to find the probability that a carton selected at random is rejected. Okay, well, in order to do that, we need to pick up on two important bits of information in this question. Those being the two parameters which allow us to define this normal distribution and its bell curve. Those parameters are the mean value and the standard deviation. And both of those things are given to us in the question. Indeed, we're told that the mean is 1000, so that's 1000 milliliters, and the standard deviation is 4. Again, that would be 4 milliliters. And so I start by making a clear note of that. The mean value mu is equal to 1000 milliliters, and the standard deviation sigma is equal to 4. Again, 4 milliliters. And now that I have those two things, I'm ready to answer the question. And so I'll write 1 here, that's the question I'm answering. To find the probability that a carton selected at random is rejected, we need to keep in mind that it's rejected if the volume is less than 995 milliliters. And so if I let the volume of milk be capital X, what we're trying to find here is the probability that capital X be less than 995 milliliters. Okay, now what I would always recommend you do is illustrate what this probability is in terms of the bell curve. Here's what I mean. If I draw a bell curve, so I've got my axis here, there we go, and a bell curve looking something like this. There we go. Now for this distribution, since the mean value is 1000, I draw that at the middle of the curve right here. There we go. That's the mean value 1000. And since we're looking into the probability that x be less than 995, I place that 995 on the x-axis, like so, 995, and this probability will then correspond to the area that I'm shading right now. There we go. So this probability is equal to this green area. And to find it, we're going to use our calculator, of course, but that doesn't mean there's nothing for us to write on our exam paper. Indeed, since this bell curve has an equation, which I'll just say is y equals to f of x, where f of x is known as the normal probability density function, or simply normal PDF. This green area, and therefore the probability we're trying to find, is in fact equal to the integral from negative infinity all the way up to 995 of f of x. And so we could write that. We could say that the probability that x be less than 995 is equal to the integral from negative infinity up to 995 of f of x. And now that that's written, I move over to my calculator, which you can see on the screen here. This is the TI Inspire CX. And to calculate this integral, and therefore this area, we use the normal CDF function, which stands for normal cumulative density function. Now on this calculator, I find that by clicking on Menu, followed by the fifth option Probability, followed by the fifth option again Distributions, and we can see it right here, the second option Normal CDF. So I click on that. And for this normal CDF function, the calculator is now asking me for the lower bound. Now the lower bound technically is this negative infinity we have here on the integral. But rather than typing in negative infinity, for all practical purposes, all we need to enter here is a very large negative number. And so I tend to write something like this. I'll write negative followed by a bunch of nines. Something like this. Negative 99999999999. There we go. That should be more than enough. Next, for the upper bound, well, that corresponds to the 995 of our integral. And so I type that here, 995. Next, we're asked for the mean value of the distribution. And as we saw previously, that's 1000. So I enter that, 1000. And finally, we're asked for the standard deviation, which we were given is 4. So I enter 4. I'm now happy with all of that, and I click on OK. And we're done. The probability that x be less than 995 is 0.10565. And on an exam paper, don't hesitate to write exactly what you see on the screen here. In other words, don't hesitate to write that this equals to norm CDF with input values negative 9999999, that's the lower bound, upper bound 995, mean value 1000, and standard deviation 4. Writing this shows the examiner very clearly what you did whilst doing this question. Next, I'll write exactly what I see on the calculator. That's equal to 0.10565. And finally, I'll round that answer to 3 significant figures to state that the probability that x be less than 995 is equal to 0.106. And that's the answer. Okay, I now move on to question 2, and I'll just draw a little separation line here. There we go. So question 2. Now for question 2, we're told to estimate the number of cartons that will be rejected from a random sample of 150 cartons. Well, for this, we're going to use the expected value formula. And I'll remind you of the formula in the upper right-hand corner, and I'll start by writing the formula, and then I'll explain a little further. The formula we need here is E equals to N times P. And in fact, I'll go ahead and box that. There we go. That's our formula for the expected value. Expected value. And here's the idea. In an experiment, if the probability of something occurring is p, then if we were to repeat that experiment n times, we could expect to see that outcome occurring n times p times. For instance, if we were to roll a standard die whose faces were numbered 1 to 6 120 times, then how many times could we expect to get a 5? Well, let's see, the probability of rolling a 5 would be 1 in 6. And so if we were to roll that die 120 times, that would mean here that n is equal to 120. And so the number of times we could expect to roll a 5 would be E equals to 120 times 1 over 6. And you can go ahead and check, but that would give us 20. So we could expect to get 20 5s. And so that's just a quick example of how we could use that formula. In fact, let me attach that to the formula itself. There we go. And so applying all of this to this second question, to estimate the number of cartons that will be rejected from a random sample of 150 cartons, well, if we're dealing with 150 cartons, that means that n is equal to 150. And so n is equal to 150. And as far as the probability of a carton being rejected is concerned, we found that in question 1. And prior to any rounding, that probability p is equal to 0.10565. And now that we've defined n and p, we can use our expected value formula to write that we could expect the number of cartons to be rejected to be equal to 150 times 0.10565. And so going back to our calculator, that's 150 times 0.10565. And we click on enter. Done. As we can see, that's equal to 15.8475. And so we could say that an estimate is that there will be approximately 16 cartons of milk being rejected. And that's the answer. That being said, I move on to the third and final part of this question, part 3, in which we're told, given that a carton is not rejected, find the probability that it contains a volume greater than 1008 milliliters. Okay, well first of all, when reading through this third part of the question, the term given that is a key term. Indeed, here it tells us that we're dealing with conditional probability, and that we should therefore be using our formula for calculating the probability of an event A occurring given an event B has occurred. And let me remind us of that formula in the upper right-hand corner. That's the formula which states that the probability that A occurs given B has occurred is equal to the probability of A and B occurring divided by the probability of B. And I'll go ahead and box that formula as well. There we go. That's the formula for conditional probability. Okay, Now that that's established, let's figure out what the events A and B would be in this question. Well, we're given that a carton is not rejected. And so if it's not rejected, that tells us that the volume of milk it contains, so capital X, must be greater than or equal to 995. And so that would be our event B in this formula. And we need to find the probability that it contains a volume greater than 1008 milliliters. So volume greater than 1008 milliliters, which corresponds to X being greater than 1008, that corresponds to the event A in this formula. So copying this formula but replacing A by X greater than 1008 and B by X greater than or equal to 995, we can state that the probability that X be greater than 1008, given that, which we write with a little vertical line there, X is greater than or equal to 995, is equal to the probability that X be greater than 1008 and that X be greater than or equal to 995, and all of that's divided by the probability that X be greater than or equal to 995. Okay, now looking at this probability on the numerator, that is the probability that X is greater than 1008 and is greater than or equal to 995, let me point out that if X is greater than 1008, then it has to be greater than or equal to 995. Indeed, it's simply not possible for X to be greater than 1008 without it being greater than or equal to 995. And what that tells us is that the event X greater than or equal to 995 is completely redundant here. And in fact, I'll write that, redundant. And consequently, this entire probability on the numerator reduces to the probability that X be greater than 1008. Since if it's greater than 1008, it's an absolute certainty that it will be greater than or equal to 995. And as a result of that, we can go ahead and state that this is equal to the probability that X be greater than 1008 over the probability that X be greater than or equal to 995. Okay, all we need to figure out now are the values of these two probabilities. And for the probability on the numerator, the probability that X be greater than 1008, I'll quickly illustrate that probability on a bell curve. So if we have an x-axis and a bell curve like this, there we go, with our mean value of 1000, which remember would be right in the middle like this, there we go, that's mu equals to 1000, and the probability that X be greater than 1008 corresponds to the area under the curve to the right of 1008. So if I say 1008 is right here, this probability corresponds to this area here. There we go. And now to calculate this area, and therefore this probability, we move over to our calculator and once more we use the normal CDF function. So again, on my calculator, I do so by clicking on Menu, followed by Probability, followed by Distributions, followed by Normal CDF. I'm now asked for a lower bound, and in this case, because the area we need to find is a right tail, and that's because the area that we're trying to find technically goes on forever on the right-hand side, the lower bound is the value of X at which this area starts, so that would be 1008. And it's the value that X needs to be greater than. So for my lower bound, I type 1008. Next, for the upper bound, well, technically there is no upper bound. It goes on forever, so it would be positive infinity. But rather than typing positive infinity, we can just enter a large number of 9, something like this. I'll just type 99999999999, and that will be more than enough. The mean value, remember, is 1000, and the standard deviation is 4. I'm now happy with all of that, and so I click on OK. And there we go. This green area, and therefore the probability on the numerator, is equal to 0.02275. And in fact, I'll go ahead and box that in green and connect it to that probability on the numerator, just to make things clear. Finally, we need to calculate the probability on this denominator here, the probability that X be greater than or equal to 995. And since we already know the probability that X be less than 995, Remember, that's what we calculated in part 1 of this exercise. We can use the fact that these two events, x being greater than or equal to 995 and x being less than 995, are complements of each other. And so the probability that we have on the denominator here corresponds to the white area we have underneath this first bell curve. And its value, well, it's 1 minus the green area we have here. In other words, it's 1 minus 0.10565. And in fact, I'll write that on the side here. This area will equal to 1 minus 0.10565. Finally, we're in a position to use our calculator again, and we can state that this equals to 0.02275 divided by 1 minus 0.10565. And so typing all of that carefully on my calculator, that's 0.02275 divided by, in parentheses, 1 minus 0.10565. I'm now happy with all of that, and I click on Enter. And we're done. Looking at our calculator screen, we can see that that's equal to 0.025437. And so for my final answer, I'll round that to 3 significant figures and state that the probability that x be greater than 1008, given that x is greater than or equal to 995, is equal to 0.0254. And that's the final answer. And there we go. That's it for this exam question on normal distributions.